This is an introduction to Euler circuit problems. This picture here is going to come up a lot for us in this chapter. It's a special problem where you imagine a city that has these bridges across the rivers. If you'll notice, there are 1, 2, 3, 4, 5, 6, 7 of these bridges. And the goal is kind of like a little game. Just simply try to cross all bridges only once. Okay, and if you want, you can pause the video and see if you can figure this out yourself. Alright, we'll come back to that bridge problem in just a minute. First of all, Euler was a mathematician back in the 1700s from Switzerland, and his name comes up quite a bit, and especially at the collegiate level and in university math classes. There's a lot of theories named after Euler, and most familiar probably is the graph theory and the Konigsberg bridge problem, which we're getting ready to discuss. Alright, with this chapter we're just looking at two basic ideas and two problems that kind of go together. First of all, if we have this system of grids or system of bridges or whatever, or roads, is there a route where we can hit every single road once and only once? And the second question, of all those routes that we could do, which one is the optimal route? Okay, which one takes the least amount of steps? Okay, so back to the bridge problem here. This really is, when you draw a diagram over this, which we'll do later, it becomes an Euler circuit problem. And again, when we have Euler circuit problems, first we want to know, does there exist a path? And then second, what's the best path that we could finish the entire course without repeating a step? So this is what we call the exhaustion requirement. And again, if you want to pause this and give it another try, you can do that. I mean, here I'll show you some ways we could start. So if we start with this bridge, maybe go across here, 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 here. Oh, okay, so we're running into problems. I can't get to this bridge over here because I'm trapped within the water. So let's just try that one more time. Let's see, erase this stuff here. Okay, so I started with the top corner bridge. Maybe I'll start with a different one this time. Let's start with the middle bridge. Go through here. Let's see if that works. Okay, this is looking good. I can go across here. All right, so I could get to this bridge, but I'd have to go through this bridge a second time. Okay, so that doesn't work either. So if you want, just keep playing around with it, see if you can come up with a solution to this. Okay, other examples and more modern examples of exhaustive routes are, for instance, mail carriers, police patrols, garbage collectors, street sweepers, and snow removals. All these types of professions, these are people that have to go around streets at an optimal route. Okay, they have to hit everybody's street, and if you can, you really want to try not to hit a street more than one time, because that's a waste of time, a waste of gas, etc., etc. Alright, here's a more detailed example with a security officer. So I want to take a patrol around the neighborhood, and it's an exhaustive patrol, which means we hit every street. Walking around on foot, we really want to try to make the best of our time here and hit every street as quickly as possible without having to double up. So first of all, is that possible? And second of all, what's the optimal route? So in the end, even if I can hit all the streets only once, what's the route that's going to let me do that the quickest? Okay, and we're going to discuss this more later in detail with a diagram, but right now I'll just show you a couple ways you could start. So if you start here on the corner, you can go a block here, maybe go down a block here, a block here, a block here, a block here, a large block here around the park, a block here, a block here, a block here. So the way I'm doing it so far seems to be working okay. It'll get a lot more tricky, of course, when I start getting in the interior part. So, okay, see what happens here? I got stuck. If I go down this way, I'm going to have to repeat one of these. So let's try that one more time. Okay, so I started on the corner for that one, and it actually seemed to be working okay. Here, let's try starting somewhere in the middle, see what happens with that. So, and I'm just doing random steps right now. We'll talk about the better ways to do this in class. Okay, so I'm already going to start running into problems here. If I go down here. If I go up or if I go up this way, either way I'm running into problems where I'm having to repeat some streets. So there are optimal starting points, especially, as well as optimal routes. So we'll talk about those later when we get into diagrams. Again, we've already kind of discussed this. This is the 7 bridges of Konigsberg problem. So once we have the 7 bridges, so they're in green over here on the left, and the goal is to try to cross every bridge once. In the next couple sections, we'll map up a diagram for this and talk about it in a little more detail. I think I've already covered it enough within this section. Alright, so coming in here with some basics before we go to the next sections. We have a couple diagrams here, and these diagrams are similar to what we're going to put on top of the bridge problem. So these are called unicursal tracings, and it's like a little simple game. You just want to see if you can try to trace the figure without having to lift your pencil. All right. So let's try figure A. Okay, so I've got a red here. I'm gonna try, and sometimes depending on where you start, that has an impact on if you can finish it or not. So it becomes a guessing game for right now, but eventually we'll talk about the best places to start for these kind of figures. So let's say I want to start up top here. So I go here, 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 here. Oh, see, I messed up, so that doesn't work out too well. Let's try that again. Now, just because you mess up starting at one location doesn't mean the entire thing cannot be completed. Voila, done. So it takes a couple of tries, and of course in the next sections we'll talk about the theorems which give us the best starting locations, and eventually we'll be able to know whether or not it can be done or not just from looking at the figure. Now let's try the second one. Let's start up top here, we go down. Okay, I'm in a tight spot. I could go across and down, but then I'd be repeating steps, so that doesn't work out too well. I'm going to try a different spot. I'm going to try one of these corners. And done. There is a noticeable pattern here between A and B. There's a very big difference in the starting points that I chose. See if you can figure out that difference, and I'd like you to try parts C and D on your own. Oh, and I forgot to say, look in the paragraph here. When we end the space when we end at the same place we started, we call that a closed unicursal training. So in A, we were able to end in the same place we started in, but in B, we did not. We ended up in a different place. So that's called an open unicursal tracing.